Welcome back class. Last time we started the filter design topic and we have learned about the basics of the FIR, finite impulse response, and IIR, okay, infinite impulse response filters, okay. And we learned that we can actually design different kind of filters from the difference equation coefficients like AK and BK, okay. Or we can also like design the filter from the Z transform, okay, the transfer function, the impulse response, and we learned about different kind of the filter structures. So we are actually digging more about this topic, and now we are actually putting about more focus on the IIR filters, okay, in this chapter. So we will learn about now how basically we can design an actual filter, okay. Last time we have just learned about the different kind of filters, okay, from the structure points of view, okay, the IIR and FIR, okay. Now there are also other categories, okay, from the working point of view of the filters, okay, which we call low pass filter, high pass filter, band pass, band stop, okay, and we can design all these filters using FIR and IIR filters. So first of all, now in this chapter we will put focus on IIR filter, okay. So if you talk about ideal digital filters, okay, our target is we go for the ideal digital filters, and a typical low pass filter, okay, which can be represented like this one, okay. And for example, if I want to write its transfer function, okay, so its transfer function will be that, let's say the magnitude is 1, okay, that the filter has a magnitude of 1, okay, uh, for which when its frequency, okay, is greater than minus omega c or less than omega c, okay, for this range, and otherwise it is 0, okay. This is the mathematical expression, okay, of writing this transfer function, okay. So remember, this is in digital form, okay. Omega is digital frequency and small omega is continuous time frequency, okay. And if you guys remember the impulse invariance, okay, that how we can convert from basically digital to analog, okay. So digital is basically sampled of the analog or continuous time frequency, okay. So this is a typical low pass filter, okay. And if you guys remember the last chapter when we actually studied about the sampling, okay, we have found that basically the impulse response of the low pass filter, okay, basically it is written as omega c over pi sinc of n times of omega c, okay. So this is basically frequency response, okay. And if you talk about time domain response of this low pass filters, it is basically a sinc, right. So basically in time domain, if we have a sinc, okay, this sinc, then in frequency domain we will get a rectangular signal, okay. So this is the basics one. So in time domain, this is the basic low pass filter, okay. And before going to the further details, I want to highlight one point here. So if you look at this time domain signal, so basically this is a non-causal, okay. You have negative part and then you have a positive part, so it's quite difficult, okay, to implement a non-causal filter, okay, in real time, okay. In real time we usually have the causal signal, okay, the signal which is only existing when you are providing the input, okay, then you have some output only for the positive values, okay. This is the one limitation of the ideal low pass filter, okay. The other thing is, if you know the low pass filter characteristics, you can design any other filter, okay. For example, if we just compare these two transfer function, okay, then we can write basically for the high pass filter, okay, my transfer function will be 1 minus of the low pass filter transfer function, okay. Like if we have 1 here, and if we subtract low pass filter from that, then we will get this filter, okay. If we subtract it, then we will get only, like if we subtract low pass filter which is only existing from this region, so then we will get only this part and this part, okay. So this is basically high pass filter. So we can design the high pass from the low pass filter, okay. Similarly, if you talk about this design, okay, which is basically band pass, okay, or we actually also call this as and this is band pass and this is band stop or band reject filter. Okay, now like here if you want to write the band pass filter, okay, so its transfer function basically it can be written as band pass filter. Okay, if we talk about in, for example, in time domain, so it will be the difference of the two low pass filter. Okay, that if we get two low pass filter with different responses, okay, then from that basically we can get this band pass filter. Okay, and I will explain this in live session. Similarly, we can get the band stop and band reject. Okay, so or like we can use the low pass and high pass filter combination and we can get the other one. So the thing is, if we know, if you can design the low pass filter, you can design any other kind of the filter. Okay, that is the key of this slide. In this chapter, we are going to focus only on the design of the low pass filter. Okay, low pass IIR filter. Okay, why? Because if you know low pass filter, you can design any other kind of the filter. Okay, so a typical low pass filter, if you talk about the design specs for a discrete low pass filter, so low pass filter, okay, usually a typical low pass filter is like the transfer function, the magnitude response is plotted like this one. Okay, so this is called pass band. Okay, like if I draw this here, so it will look like this one. Okay, so this is called pass band and this is called stop band. Okay, and this difference between pass and stop band, this is called transition band. Okay, and the frequency at which basically pass band is ending, this is called pass band frequency. Remember, we are in a discrete domain. Okay, okay, now we want to design basically for the discrete time. Okay, so first of all we will design in analog domain or continuous time domain. Okay, or in this frequency. First we will design in this analog filter, then we will convert that filter to the discrete time. Okay, this frequency domain. Okay, so this is the continuous time. So this is the pass band frequency and this is the stop band frequency. So from this frequency, stop band is starting, and in between them we have this transition band. Okay, and if you talk about the magnitude, okay, so like an ideal filter is like we have 1 here and then it becomes 0. Okay, but in real time there will be some fluctuation like here. Okay, so the top value we like write is as 1 plus sigma 1 and 1 minus sigma 1. So this is the range basically, the sigma 1 range, okay, which is basically ripple or fluctuation in the pass band. Similarly, we could have fluctuation in the stop band, and this stop band fluctuation is written as sigma 2. Okay, and if we convert this continuous time to discrete time, which is very simple, we use this impulse invariance relationship. Okay, so this continuous the pass band, okay, cutoff frequency, it will be converted to this omega. Okay, so this is the pass band cutoff frequency, this is the stop band cutoff frequency. Okay, and this is basically your sampling frequency, if you guys remember. Okay, this is your sampling frequency. So sampling frequency should be this one to avoid the aliasing in the design of the filter. Okay, so these are the basically the design specs and design equation. Okay, for example, if you talk about transfer function, so its magnitude is in between these variables. Okay, so it's greater than 1 minus sigma 1 and less than 1 plus sigma 1 for which frequency? Up till pass band frequency. Okay, when omega is less than or equal to pass band frequency, and when omega is greater than, okay, stop band frequency and less than sampling frequency or pi. Okay, so then my magnitude is basically sigma 2. Okay, and if you want to talk about the dB scale, okay, so we can take the basically the normalized value, okay, actual transfer function value with respect to the maximum value. Okay, so that will be just the dB scale plotting. So these are the basically the design specs, design equation for the low pass filter. Okay, and now if you talk about its transfer function in more details, Okay, before going into those details, so typically now if we look focus on this slide, so the design parameters for analog continuous time filters are ripple in passband, ripple in stop band, passband cutoff frequency, and stop band cutoff frequency. Okay, these are the main design parameters. So if you know them, you can design any kind of filter. But in some books and in some software like MATLAB, they use another criteria which is called basically the relative ripple in passband. Okay, so instead of like sigma 1 and sigma 2, they are using a term of relative ripple. Okay, so like here we have 1 plus sigma 1, 1 minus sigma 1. So MATLAB basically, for example, it use relative ripple in passband. So we can calculate relative ripple from these values basically. Okay, and similarly it define the relative ripple in stop band. Okay, so when we actually you design a filter in MATLAB, so you guys will come across these parameters. Okay, that what is the relative ripple in passband. So same concept. Okay, what is the ripple in passband and what is the ripple in stop band. Okay, but we define them in dB value. Okay, using these relationships. Okay, and the general, now in the low pass filter design, there are many other kind of filter design. Okay, the first one which we are going to discuss is Butterworth low pass filter. Okay, so this is the magnitude scale response of a typical Butterworth low pass filter. Okay, and if we plot this, it will look like this one. Okay, here n is the order of the filter. Okay, and omega c is the cutoff frequency of the filter. Okay, for example, this is the cutoff frequency. So here we will have the pass band frequency. Okay, and here we will have the stop band frequency. Okay, so cutoff frequency is basically greater than pass band frequency and less than stop band frequency. Okay, typically we define the cutoff frequency as the 3 dB frequency or corner frequency. Okay, so it's a point where actually the magnitude from the top is reduced by 3 dB point. Okay, that is the point. Okay, where we are actually getting the magnitude reduction of 3 dB. Okay, and here you can see that, for example, if you have lower order filter, okay, so you are getting a more shallow response like this one. Okay, and as the order increases, okay, your filter is transition becoming more and more sharp. Okay, so this is the relationship. And if we go for infinity order filter, very high order filter, okay, we will get an ideal filter, okay, which will look like this one. So these are the characteristics, okay, about the design of a Butterworth low pass filter. We will see more details and relevant example about this in the live session. Thank you very much for your time here.